So our topic is over deriving heart rate estimations from physical activity. I'm Adam, that's Carl, Roger, and Zalou. So from our previous work, we know that motion and heart rate levels are correlated. Motion isn't the only thing that impacts heart rate, but it is a major factor that impacts that. So we'd like to model heart rate based on these activity levels. So for our project, we compared a simple linear regression, a more advanced linear regression, and a couple neural networks that we tweaked to fit our needs. And so potential applications for a model like this would be that you might be able to reduce power consumption in a wearable device if you sample the heart rate sensor less frequently, because these typically take more power consumption. And so if you can use a cheaper sensor, that'd be better in the long run. Additionally, you might be able to compare this heart rate estimate with the ground truth estimate, or the ground truth measurement, and look at the difference, and that might give you some indication of wellness, where if they start to diverge, something might be physiologically wrong. And finally, you can also indicate to a user a certain level of activity to reach a desired heart rate if they're interested in very specific training. So a little bit of literature review. We did find models that had done similar things before, but none of them quite fit our needs. So the first was a Kalman filter. They did very well and had really good results, but a Kalman filter is more for error correction, and so you need the ground truth and the accelerometer at the same time. So if you take away the ground truth like we wanted to, you'll quickly diverge, and then your estimates basically increase exponentially or decrease exponentially. So it didn't really work for us. Next we had a model that was very, very nice, but it was a bunch of really intense equations. They even went so far as to estimate the lactase impact on heart rate, which was getting much too fine-grained. It was difficult to tune that model. And so lastly, we found another team that took a control theory approach and looked at differential equations for modeling heart rate. And again, they found good results, but it was also difficult to implement and tune. So we decided to go with our own methods. So to start off with, we collected sensor data for each of us over 2 days. So we had 8 sets of data. We did it over 2 days so we could predict one day from the other. And we started off with a simple linear regression. So we take the entirety of day 1, calculate weights, and then apply those weights to day 2 for prediction. This basically just shifts the activity waveform upwards so that both the signals are on top of each other. It's not a very good predictor of heart rate. And we got similar results no matter how many previous activity samples we've used. We used 3 for the graph I'll show you, but we got similar results regardless. So this orange line is the activity signal. That's the vector magnitude of all 3 axes of the accelerometer. And so as you can see, it's not a very good predictor, but you can see the different periods where we're walking, running, and climbing the stairs.
So to overcome the poor performance of a single linear regression model, we decided to implement an adaptive linear regression model that basically changes when we detect an activity level change. To do this, the model is revealed when we detect an activity change by using the next n heart rate. And the problem is that because of the heart rate changes are different of the activity level changes, we can build models from noisy data, meaning in wrong estimations. So to deal with this issue, we implemented lower and upper bounds that basically means that how much time we can remain with the same model before we force the model to be changed, and how often can we build new models. As you can see here, the orange is our estimated using the adaptive linear regression model with those bounds, and the blue one is the ground truth. And as you can see, it behaves much better than a single linear regression model.
So our problem is basically a time series prediction problem. So there's one kind of neural net which is called the Knox model. It is suited for predicting time series. Basically, it takes an exogenous input. In our case, is a heart rate, is a activity level, and we want to predict heart rate from that. We have 2 days data. We change the model with the data from the first day and to predict the heart rate of the second day for a model for 1 person. And so this figure shows the structure of the Knox network. So basically X here is the external input, which is the activity level in our case, and the output Y is the predicted heart rate. So what's special about this neural net is the output, this is a closed loop. The output goes back to the input. So this network keeps a memory of the past D times, which is shown in this equation. So the heart rate at time t is a function of the past D times of output, which is heart rate, and the past D accelerometers, basically activity level. And so this model is still, it works fine, but if we want to predict heart rate in a very long time, like we have data of more than half an hour, the activity level is, that's not enough information to predict the heart rate. So we need to somehow to adjust the model, adjust the prediction error. So what we need is to sample the ground truth data in some time interval. So there are 2 approaches to do this. The first is to sample on a constant time interval, and another is to sample the ground truth adaptively. Basically, it tells you when the network is going to take the ground truth data and use that as the input for the neural net instead of using the predicted value given by the network output. So this way it dynamically corrects the error. So here shows some results. So the first figure is, as you see, the orange is predicted with the Knox model, which you can see at the end it diverges from the ground truth data. So the second figure shows the predicted with the error correction based on a constant time interval. And the third one is the correction based on the adaptive selection.
Aggregating all the results into a table, you can see 2 main trends from this table. Here in the first column is the model we use, which starts with a basic linear regression, goes down to the more complicated ARCS model. So the trend is increasing in complexity. The second trend that can be observed is in those second 2 columns. In the third column there, it's the percent of ground truth we're using to use to make a prediction in the model. So the trend here is typically as we use more of the ground truth, the error rates drop. The only case where this doesn't hold is from a basic linear regression to the first adaptive linear regression model. Error actually increases, and this we can explain due to the noisy activity level data, where the adaptive model basically just picks the wrong activity level and tries to make a prediction based on that, so it has a very lousy estimate on that. And just wrapping it all up, in conclusion, we successfully modeled heart rate off activity level. As said just previously, dynamic models tend to work, well, did in this case work better than the fixed models we had deployed. So this allows for different responses according to initial heart rate, which means the models won't just use a baseline heart rate through the whole calculation. It'll look back at what its most previous history is in heart rate. And another nice benefit of our dynamic models is they also kind of automatically account for fitness level. So it's not an explicit parameter that needs to be supplemented into the model. The last point here is about 7 times less power consumption. We calculated this doing some basic power modeling based off some data sheets between some PPG sensors and accelerometers. So it's kind of just comparing the sensors to sensors in that case, where we get about a 7 times improvement in power.
So that's what we got.
Okay, I have one question. So the results are any one of these. So this is on so which part is training, which part is testing? So you said you're going. So is this on the test data?
Yeah, this is all the test data. Periodically, we will sample the ground truths. There's bits of training data sampled in there. That's the 12%. But these are all models that we trained on day 1 exclusively, and then start to predict on day 2.
For the same person?
Yes, for the same person. And then as soon as we hit either the model said, hey, I need to resample, or we hit the sampling interval, we would sample the ground truth for a few seconds and then go back to predicting.
How did you determine that you need to sample?
So there are 2 approaches. One is you sample based on a constant time interval. Like every 40 seconds, you sample 5 seconds of data. Another is sample adaptively, which is based on the previous proposed linear regression model, adaptive linear regression model. That tells you when do you need to sample, which is basically based on activity change.
Yeah, so if we see a significant enough change in activity level and it's sustained, then we know it's not just a spike, and then we'll repredict the model. Did you have a question?
One question is that if you learn from, let's say, 20 seconds, and you predict the next 20 seconds, suppose in the next 20 seconds, you begin to rain during like the 10 seconds during in the middle, suddenly the heart rate increase. Can you predict this?
Yeah, so that's basically what's happening here. We follow the same protocol on both days. So we've trained it on sitting and running data, so it knows these different activity levels. And so you're right, if we just trained on one level, like if we trained on sitting and then suddenly we did start running, that could be an issue. But then when we detected that we did start running, we say, okay, well now I need to update the model. So we sample the ground truth for a little bit, and then it'll track with that. And that's the issue we saw with the linear regression, where if we never take into consideration what we're doing, you'll just see this crappy flat line. But once you start considering the various activity levels and where you start from, then it's different. Because you can see the response for this activity, well, in terms of what the accelerometer saw, this and this should be the same. But based on the initial heart rate, this spike is higher. So the model can adapt for that rather than making these 2 short bumps like we see here.
Question?
Yep.
What does the activity signal look like?
It looks like this first one. It's a little bit shorter, but when it's by itself, these are about at 0.2, which is supposed to represent walking, and then this is around 0.8, which represents jogging. So it's just the vector mean of of all 3 axes that has been bandpassed to remove the effects of gravity and any non-human factors, like if you're in a car or something.
Okay, so it essentially looks like the heart rate beat signal.
Yeah, and so we know that it's not super different shapes to start off with. There are spikes that correspond with those heart rate increases.
Okay, so we are out of time, so let's move on to the next group.